I'm joined by Jack Pearson, who is one of our consulting specialists in our CES group. So it's nice to meet you. So we're going to roll into this webinar. So we're going to turn off our webcams for now. Before we really get into any of the technical content of this webinar, we ask that you review this disclaimer for a brief moment. Okay, so when talking about optimizing our steam system, there's a couple different levels that you need to look at. So we have our steam generation at our boilers, and we have our steam distribution system. And the whole goal of our steam distribution system is to supply dry steam to our equipment in order for it to operate efficiently. And with that equipment, we want to be able to drain that condensate as fast as possible to maximize our heat transfer and equipment performance. And to optimize overall energy consumption and optimize our system, we want to be able to return as much condensate as possible. So today we're going to be focusing on that lower section of returning that condensate and recovering that energy. So with condensate drainage and recovery, what are the goals? Well, the first goal is to drain all of our steam using equipment efficiently and effectively. And there's a few different points to that. The first is our condensate discharge location design. And that involves things like our drainage devices. What type of steam traps am I using, or do I need a pump to pump condensate out of this equipment? And we want to mitigate any steam-induced water hammer in our condensate return line. And ultimately, we want to recover all of that condensate wherever it's economically viable. So looking at the condensate recovery economics, there's a lot there in our favor. So here we have a boiler where we're producing steam. We're sending that steam throughout our plant, and we're using the latent heat of that steam to heat our product. And about 70% of that overall steam heat is going to our product, and the remaining 30% or 10 to 30%, depending on our pressure and our system, remains in that condensate and flash steam generated after we give off that heat. If we're not recovering that condensate, that's 10 to 30% of total heat that is immediately lost out of our system. So if we can recover that condensate and that flash steam, there's a lot of value there. First being, we can reduce our overall boiler fuel consumption, which ultimately saves us money. It also recovers our boiler chemicals and our water treatment. It reduces the demand of makeup water, so we're saving that water cost, as well as it reduces any cost associated with dumping that condensate to sewer or any treatment cost associated with that drainage. Other benefits include lowering our CO2 and other emissions because we're burning less fuel. We're also limiting atmospheric steam vents, which can be an eyesore to a lot of people. And we also are able to improve the work environment for those who are working in our plant. If we look at that improved work environment, what are the problems caused by unrecovered condensate? Well, first you have decreased visibility. And this may be a very common sight that you may see throughout your plant where you have large steam plumes down at grade level from condensate being discharged to atmosphere. This is also increasing noise in that area, which can be uncomfortable to the workers. It can also create slipping hazards by having condensate on the ground, which can form algae. And also in low temperature environments, in northern climates, we can have freezing, which can also create a headache for plant personnel. So how can we take care of these problems caused by the unrecovered condensate? Well, we can utilize things like tracing collection manifolds to collect those tracing lines, which are very prevalent in many plants and are often discharged to grade. We can collect those and return those to a common header. And we can also use condensate recovery stations. So these things ultimately give us and the people working inside our site peace of mind and having a more safe work environment. Now, before we really dive into condensate recovery, there's a very important steam basics topic that we need to talk about, which is the topic of flash steam. Now, many people will see a steam trap discharging to atmosphere, and they'll see a large steam plume coming out of the steam trap, and they may think that this steam trap is leaking. Well, no, your steam trap is not leaking. It's actually just flashing. So as that condensate discharges to atmosphere, a portion of that will flash into steam, and that's the steam that we're seeing here, not necessarily a leaking steam trap. So now let's look at, why does flash steam happen? If we look at steam at 100 psi, we're over at the left, or the dot on the right-hand side of the page. As that steam gives off its energy, it's going to turn into condensate. And at 100 psi, that condensate will be at 338 degrees as it's being discharged at the steam trap. Now, if we're discharging that to atmosphere, condensate can only exist at atmospheric conditions at 212 degrees, and it can only hold 180 BTUs. So that condensate has an additional 129 BTUs per pound of energy, which is immediately released into flash, and that's what we see coming out of our steam trap. And you can calculate the amount of flash that you're seeing from your steam traps using the TLV online calculator by entering in your condensate pressure, your condensate load, and what your recovery line pressure is to come up with a ratio of flash steam to condensate that you will see coming out of your steam traps. Now, when we're discharging those steam traps into a condensate return header, our header is going to look something like this, where we have a very large volume of flash steam with a relatively small volume of condensate. Now, if we break that down, looking at the mass and the volume, we see something very interesting. So here, if we look at condensate being discharged from a 150 psi steam trap into a 30 psi return line, the mass of that condensate is about 90%, where the flash is about 10% of the mass. But condensate and steam have a very different specific volume. Condensate is very dense, where flash steam has a very, very large volume. And by volume, only about 1.6% of the volume is actually condensate, whereas 98.4% of that volume is steam. So while the mass of the flash may be very small, it's the volume which can be very large, and something that we need to take into account. And as our pressure differential changes, so does the amount of that flash steam. So you can see here, if we have a very high condensate recovery pressure, we have a very small amount of flash steam and a very large amount of condensate. That's fairly uncommon to see that type of high pressure condensate return system. It's much more common to see a low pressure condensate return system with a large amount of flash and a very small volume of condensate. So this is going to be very important as we look at different types of condensate return line systems. So let's dive into a little bit behind condensate system designs. And there's really three different types of condensate lines that we need to consider. So here's a system with our steam equipment, our steam trap, and a condensate return line. So the first type of lines that we need to consider are two-phase condensate lines. And there's actually two types of two-phase lines. The first being non-flashing. And this is where our condensate is still at the same upstream pressure as our steam line. And those are the steam lines between our equipment and our steam trap. So here it's at the same pressure, and it's moving at a relatively slow velocity between our equipment and our steam trap. Next type of two-phase line is going to be our flashing two-phase condensate return lines. And these are the lines downstream of our steam traps, where the condensate is traveling from a high pressure to a low pressure through the steam trap due to differential pressure. And now we have both flash and condensate, like we saw in our earlier discussion of flash steam. Next type of condensate would be a single phase condensate return line, or a pumped line. And this is where we're using condensate pumps to boost the pressure of that condensate and send it into something like our boiler. So if we look at our two-phase condensate return line system, we have that two-phase flashing steam, and those steam traps are providing the differential pressure to move the condensate from the steam trap back to our main point of collection, usually near our boiler at our boiler feed water tank. Now, some advantages to this type of system is that it's reliable. It's fairly simple. We're relying upon those steam traps to move that condensate back to the point of collection. And because of that, we do not have any need for pumps or any special equipment to move that condensate. It's all moved by the differential pressure associated with those steam traps. Now, some downsides are that it does require a much larger condensate return line size because we have to deal with that large volume of flash steam. And the design of our piping system can be a little bit more complex because we have to deal with that two-phase flow. And if it's not designed properly, we can experience things like water hammer. If we're trying to lift that condensate and flash steam overhead, it can cause some problems if not designed properly. Now, looking at a single-phase condensate return line, we're still going to have flashing condensate lines between our steam trap and some type of equipment like a vented condensate recovery station. In this case, we're showing a TLV PowerTrap. From that pump system, we are then pumping that condensate over a long distance to our main collection point. And here, basically, we're needing some type of pump to move that condensate over long distances or over high lifts. Basically, we can't just rely upon the steam trap to return that condensate all the way back to the point of collection. Now, some advantages to this are pumped condensate return lines are much smaller, which can make it much more economical to return condensate over very long distances. But you do need pumps in order to return that condensate. And in this type of system, our flash steam is either lost or we're going to need additional equipment to recover that energy from that flash steam. And that's something that Jack is going to go into detail later on in this presentation. So now let's look at some economic numbers and some factors behind condensate recovery economics. So first, we're going to look at what we would call a closed condensate recovery system. So this is our two-phase system. And we're just going to make the assumption that we are recovering all flash and condensate back to our boiler. So the economic factors that we'd look at for condensate recovery would be things like our steam line pressure and our condensate recovery line pressure. We'd look at what the temperature of our makeup feed water is to the boiler, as well as looking at things like our fuel type, our fuel cost, and our boiler efficiency. And ultimately, we want to look at the amount of condensate that we're returning back to the boiler. So if we look at a sample calculation and say that we're saving 1,000 pounds of condensate from a 100 PSI system going into a 20 PSI condensate return line, typical makeup water temperature of about 70 degrees with natural gas and a typical boiler efficiency and average fuel cost. For 1,000 pounds of returned condensate, we could be recovering about 267,000 BTUs an hour. And based on our fuel cost and boiler efficiency, that could equate to about $14,000 a year. So there's a lot of money there to recover just 1,000 pounds an hour of condensate. And the fuel reduction of that is about 20% of the fuel reduction that went into that 1,000 pounds of condensate. So if we're only generating 1,000 pounds of steam at our boiler and we're recovering 100% of our condensate, we're reducing our overall fuel consumption by 20%. Now, if we're generating 10,000 pounds of steam an hour and we're recovering 1,000 pounds of condensate, we would still be reducing our overall fuel consumption by about 2%. But still, there's significant fuel reduction savings possible by recovering that condensate and flash steam in a closed type system. Now, if we look at a single phase condensate return system, or we would call an open condensate recovery system, this is where we're recovering the condensate, but we may be losing that flash steam. And there might not be many options to recover that flash steam. And if we assume the same type of economic factors, we're still recovering about 130,000 BTUs an hour in energy associated with the heat of that condensate, which is almost $7,000 a year for 1,000 pounds of condensate. But here we're still losing about 137,000 BTUs an hour to the atmosphere. And that just might be a natural loss that we cannot recover, but there's things that we can do to try to recover that. So now we can take a look at condensate return line sizing and what things do I need to consider when sizing a condensate return line for both single and two-phase. So a single-phase condensate return line would be something coming off of a mechanical type pump like a TLV PowerTrap or some type of electrical pump. And the considerations that we need to take into account are that we are only pumping our condensate in these lines and that we do not have any flash. Typical velocities in these types of lines are going to be something around 3 to 6 feet per second. And we need to take into account things like pressure loss. And with a mechanical pump, we want to take into account our instantaneous discharge velocity, which could be much higher than an average discharge velocity. We also need to think about what happens if I have future expansion. We want to make sure that our condensate lines are properly sized, that we do take into account any future expansion so they don't become undersized in the future. Now looking at two-phase condensate return line sizing, these are not going to be as simple. And there's a lot of things that we need to take into account here. With a two-phase condensate return line, we need to take into account the flash and the condensate in that line sizing. And our overall velocity in that line is really going to depend on the ratio of that flash steam to condensate. If we have mostly flash steam, we can deal with a much higher velocity. We might be able to run this condensate return line at 50 to 80 feet per second. But if we have a higher volume of condensate, then we're going to need to slow that velocity down much closer to a pumped line. And if we get a high condensate return line velocity, we could experience problems like erosion, water hammer, and excessive pressure loss. So our recommendation when sizing a two-phase condensate return line would be to consult with your professional engineers and pipe designers to determine what the acceptable velocity is based on your flash and condensate ratios. Now you may ask yourself, well, can I mix my pumped condensate and my two-phase condensate into the same condensate recovery line? Well, the answer there is only if you want water hammer. So if we look at an example here of pumped subcooled condensate return lines coming in contact with hot flashing condensate, you can see that we're forming pockets of steam in that line, which are going to rapidly collapse and cause water hammer. And this is what we call steam-induced water hammer. And this is a very common phenomenon when we have a subcooled condensate line and we're injecting in either a steam trap discharge or a two-phase condensate return line into the same line. We get those pockets of steam which collapse rapidly, which is going to cause problems with damaged insulation, damaged flanges and connections, and just cause overall problems and reliability issues throughout your site when trying to return that condensate. And we won't go too much into condensate return line water hammer, but we do have an article attached to this webinar, which was published in Chemical Engineering Progress, written by Jim Risco, entitled Stop Knocking Your Condensate Return, where he goes into detail about this topic. Now, you might also say, well, we have problems with high condensate recovery line pressure. How do we fix that to increase our condensate recovery? Well, let's look at problems caused by high condensate recovery pressure. So here we have a steam trap fighting against a high back pressure, and a high back pressure is going to cause a reduction in steam trap capacity, which could back up condensate. Also, high back pressure will cause thermodynamic disc traps to remain open and blow steam into your condensate recovery system. This is going to further lead to high back pressure and also lead to problems like water hammer. And also, if our downstream pressure, our return line pressure, becomes greater than our upstream pressure, we could have a no-flow scenario where we're getting now cold process temperatures and we're backing condensate up into our coils and our heat exchangers, decreasing the overall production and performance of our site. So you might ask, well, what causes this high back pressure in my condensate recovery system? Well, part of it may be your system design pressure. Your condensate may be going to something like a flash vessel or something else, which is actually controlling the pressure in that line to a certain pressure. You also have factors like vertical lifts, where you're lifting that condensate overhead. And as a general rule, for every 2 feet of lift, you're going to increase your pressure seen at your steam traps by about 1 psi. You also need to take into account undersized piping. Many systems that we see have been expanded over time, but the condensate return line system has never expanded, so you continue to add more and more condensate and flash steam into a system that just simply wasn't designed for that. And that causes high frictional losses, which increases your back pressure seen at your traps. You also have problems with leaking steam traps, leaking live steam into your condensate return line system, increasing the pressure, as well as having hidden problems like open bypasses, which can be a significant contributor to live steam in your condensate return line. So what are your options for dealing with high back pressure? Well, the first thing you could do is raise your steam supply pressure, but that really doesn't seem very practical. Your second option is to reduce your back pressure. And the most effective way to do that would be to manage your steam trap population, close your bypasses, and if that still does not alleviate the high back pressure, you could look at venting flash steam in certain areas and pumping that condensate back. So here we have our closed condensate recovery system. We may have high back pressure preventing return. We would install a mechanical style pump where we're venting off the flash, and which reduces the pressure seen at the trap, allowing our steam traps to operate, and we're still able to recover that condensate. So now we're going to get into a little discussion about condensate recovery pumps. And really with pumps, you have two options. The first being electrical style pumps, the other being a mechanical or a motive pressure powered pump. So if we look at a typical electrical condensate pump, it's going to look something like this in many sites. You have a condensate inlet, a vent, your pump discharge, as well as an overflow loop. And there's a lot of things we need to consider when selecting this type of pump. So the first thing that we need to consider is the design load versus the actual load. We also need to look at our total dynamic head as well as our total discharge pressure. We have to match all of that to our pump curves, as well as making sure that we have a net positive suction head on that pump. We need to calculate our available suction head, as well as what suction head is required. And with electric pumps, we may run into problems with high temperature condensate return, which causes problems with cavitation and pump seal failure. Electric pumps can also be very sensitive to TDH calculation errors, and sometimes we just don't have enough NPSH available. And we also require electricity in multiple trades to get this type of condensate pump installed. Now, I'm not going to get into a full detailed discussion about electric pumps, but you can find a recorded webinar on our website by Jim Risco comparing condensate recovery pumping options. So both mechanical and electrical. And you can find that on our TLV website under our webinar link. So I will get into a little bit of a discussion about mechanical style pump traps. So here's a typical vented condensate recovery station where we have multiple condensate sources discharging condensate into a two-phase condensate header. We're venting off our flash, and then we're pumping single-phase condensate into a single-phase return line. And that's all done from a motive steam supply. So let's look at how this type of pump works. So we're going to have condensate come into a receiver and drain down into our pump. Our pump is going to gradually fill over time, and any flash steam in that line is going to go out our flash vent. Now, as that condensate level rises in the pump, we're going to be displacing any vapor in that pump back up to our condensate receiver. So our condensate level rises over time. Eventually it trips a mechanism which injects a high pressure motive or air source into that pump body, which pushes that condensate out of the pump and into our single phase condensate return line. During that time, any condensate that comes into our receiver and down to our pump is stopped by an inlet check valve, and condensate begins to back up into our receiver. So this receiver acts as a backup volume. At the end of the discharge cycle, any high pressure motive steam in that body is exhausted back out our balance line into a reservoir, and then condensate again flows into the pump. So this is a cyclic type operation for this type of pump. If we look at the internals, you can see here it has a snap action mechanism. And as that float rises, it's going to trip a mechanism which simultaneously closes an exhaust valve while opening a motive valve to allow high pressure motive to push that condensate out of the system. As that float drops, the mechanism snaps again, closing the motive valve, exhausting any high pressure motive, and then condensate flows back into the pump. Now, what are the advantages to this type of mechanical power trap? Well, one is that they're cavitation free. So whereas with electric pumps, we have to be very careful with our temperature and our NPSH, we can recover high temperature condensate using a mechanical pump with zero worries about NPSH. We also have a very low fill head needed to fill these pumps. So our TDH calculations are very simple. These are also intrinsically safe as they're steam powered, they're non-electric, and they're fairly easy to size and select. Another advantage is that we don't have to worry about overheating with electric pumps, which gives us the advantage of being able to size these with a very small sizing factor to maximize economics. And if you have any type of application where you need a condensate recovery pump, you can work with TLV and we can help you fill out what we call a condensate recovery application, where we would gather the information about your application and provide you with a recommendation for that condensate recovery package. So now I'm going to flip things over to Jack Pearson, and he's going to take us a little bit more into the flash recovery side of things.
Thank you, Drew. So far we have discussed the importance and the theory behind recovering condensate. And along the way, Drew has mentioned the possibility or need to vent flash steam, whether it be because of high back pressure or water hammer issues. And what we're going to explore next is what opportunities might we be missing when venting this flash steam? Can we reuse this flash or at least recover the energy? So let's take a look. Here are some sites commonly seen at many facilities. Not terribly attractive, but often considered necessary, and not a lot of consideration is placed on whether an alternative is available. Many people, or most people, recognize that there is heat energy here, but what can be done about it? How can we keep that heat energy and that condensate in the system? So why do we recover flash steam? Well, the reasons really aren't that different from why do we want to recover condensate. Top of the list, of course, is cost savings. There's a lot of latent heat in that flash steam that if we could keep it in the system, that's a lot of energy that we would prefer to keep in the system if possible. Recovering condensate that is otherwise lost. Because what is flash steam but vaporized condensate? Safety, open steam vents can be dangerous. They can lead to decreased visibility due to steam clouds or steam plumes. And in cold environments, this can cause slipping hazards on walkways or stairwells, especially if condensate is carried over in the vent and can rain back down, which also could, of course, lead to a potential burning hazard. And vent elimination is good also because it can provide a positive environmental impact. Recovering that condensate and also eliminating vents creates just a nicer work environment. So let's take an up-close look at an example of an installation that would result in vented flash steam. This really is no different than some of the examples that Drew showed earlier, just with a bit more detail. So we start by bringing our steam into our heat exchanger, which is going to give off energy to our process flow, whatever it might be, which in this example, in this case, is on the shell side of our heat exchanger. As we give off energy to our process, we're going condense that steam and send the condensate down through our steam trap. As the condensate moves through our steam trap, it's going to experience a pressure drop, and in doing so, it's going to flash. So we now have two-phase flow exiting our steam trap, which is going to enter our atmospheric vessel, allowing the condensate to fall down to our PowerTrap pump, which will then be pumped back to our condensate return line. And that flash steam is going to be sent up our vent and rejected the atmosphere. So what are some of the methods for recovering this flash steam? How can we go about keeping that energy in the system? So number one is going to be a pressurized flash vessel where we can actually reuse some of that low pressure flash steam. Next option is going to be a vent condenser where we can take that flash steam, condense it, recover the energy to keep in the system, as well as the condensate that was once being sent through the vent, and keep the condensate as well as that energy in the system. And the last option here is going to be a steam compressor, where we can actually boost what was once steam that was at a low enough pressure that it was considered to be unusable, and we can boost it up to a higher, more usable pressure. So here's a look, an overview of a flash recovery system. And what we're going to do is break it down into pieces and review each of those pieces to get a more clear understanding of how it works within the system. Those pieces are going to include our flash vessel. They're going to include our low pressure steam users, our PowerTrap condensate pump, and our vent condenser. So first up, let's dive into our flash vessel. So the start of this is going to be our high pressure condensate, our two-phase flow, which is going to come in and enter our flash vessel. As it enters our flash vessel, the velocity is going to slow, allowing those two flows to separate from one another. Condensate will go down and out the bottom of the vessel. It's going to go through a steam trap and once again take a pressure drop, which means that it's going to flash once again. So it's exiting as a two-phase flow from the steam trap. And the flash steam is going to go out the top of the vessel and supply steam to our low pressure steam header, which is going to be going a particular direction. Now, the quantity of flash steam that we have on hand generally is not going to be enough to fully supply our low pressure steam header, which is why we also have our high pressure steam header right here that we can use to supplement our low pressure steam header. So that allows us to maintain a minimum pressure in our low pressure steam header. So any additional steam that's needed to fully supply our low pressure steam header is going to be sourced from a high pressure steam header. So let's take a closer look at what's going on inside our flash vessel. So this gives you a clear look at how the flows are separated. Our flash steam can exit the top and be sent to be used elsewhere, and the condensate can be drained out the bottom to be sent to a different location. This also gives you a good picture of how we can bring two-phase lines, our flash and condensate, together with pumped condensate. Drew warned us earlier about the risks of bringing those two lines together, risks being a potential for steam-induced water hammer, but this is a way that we can safely bring those flows together while mitigating that risk. So a quick look at sizing for a flash vessel. The goal here is to slow the velocity enough to allow for separation of the condensate and the flash steam, or to slow it enough for the condensate to fall out from the flash steam. So we're going to size the vessel large enough. We're going to have a large enough diameter to slow the velocity to about 10 feet per second, which will allow that to happen. And then once we've accomplished that separation, the steam can be ramped back up to velocities seen commonly in most steam lines, which is going to be about 100 feet per second. So to look at it a different way, looking at the system as a whole, starting at the top left there, we have our high pressure steam line, and we're going to supply our high pressure steam using equipment. That condensate is going to be discharged through steam traps, which of course is going to flash into our high pressure condensate return header, which is going to drain into our flash vessel. It does as we described before, separates the flows. We can get rid of the condensate and recover it somewhere else. And then the now low pressure steam can be used in our low pressure steam header to supply our lower pressure steam using equipment. Another note that's important to make here, let's say for an example, our high pressure steam line is at 150 psi and our low pressure steam line is at 50 psi. That means that our flash vessel, because it's open to our low pressure header, is also at 50 psi, and our high pressure condensate return line, which is open to our flash tank, is also at 50 psi. So it's important to ensure that our high pressure steam using equipment maintains a pressure above that 50 psi to maintain positive differential and ensure the condensate can drain down to our flash tank. If we run into a scenario where we don't have that differential, that's when we have to start consider using something like a PowerTrap instead of using a steam trap in those instances. Moving right along here, we have now fully supplied our low pressure steam header, and we're going to route that steam over to our low pressure heat exchangers. So we can zoom in on our low pressure exchangers, and we're going to send that low pressure steam over to our equipment. We're going to use that energy in our steam, condense it, and send it through our steam traps, which is going to discharge into our low pressure condensate header, which again is going to be two-phase because we're going to flash across those steam traps. I'm not going to delve into the complicated discussion of effective process equipment drainage, but we did an excellent webinar called Optimizing Steam Process Heating Applications. It's available on our website that does dive into this and gives a lot of good information on how to ensure we're effectively draining our process equipment. And another option that we have is an excellent article written by our president, Jim Risco, that talks about some of the complications that we have to consider to overcome drainage issues in some of our process equipment. Okay, so we have now drained our low pressure heat exchangers, and we have sent that low pressure condensate to an atmospheric condensate receiver. So we're going to zoom in on our condensate receiver, or our PowerTrap skid. We have sent our two-phase flow into our atmospheric receiver. And just as before, the condensate and flash steam are separated. The condensate is drained down to our PowerTrap, and that's returned to our condensate header. And the flash steam is sent up our vent, which often is considered the end of the line. That flash steam is considered too low pressure to be used for any real purpose, and it's just kind of a necessity of the system, and this energy and condensate is lost. A quick look at sizing for atmospheric receivers, and it's actually very similar to sizing of a pressurized flash vessel. Really, the goals are the same. Goals being to slow the velocity enough to separate the flash steam from the condensate. So same velocity goal, 10 feet per second, allows us to separate those flows. And the vent velocity, we want to maintain a maximum. So we want to maintain less than 70 feet per second. And this is to minimize the potential for condensate carryover and the risk of sending condensate up the vent, which would then rain down, which is not what we want to have happen. It's also worth noting that pressurized vessels, well, they're often larger than pressurized vessels because of the larger volume of atmospheric steam. Okay, flash steam recovery. Let's take a look at the TLV SR series flash vent condensers. So in the previous model that we looked at, you saw the PowerTrap skid, and we were venting that flash steam to atmosphere. And you can see in this diagram, in this model, that we plugged in a new piece of equipment where we are going to route our flash steam to. In this equipment, we're going to run cooling water through an internal coil, excuse me, bring in cooling water in the bottom, cold cooling water on the bottom, and it's going to be discharged from the top at a hot, much hotter temperature. Along the way, it's going to collect energy from our steam. It's going to condense the steam, and we're going to send that condensate back down to our PowerTrap skid to be recovered, to recover that condensate. So taking a close look at what is going on inside this vent condenser. So you can see the steam inlet on the top left there, supplying the flash steam to the shell of our exchanger. And we have our cooling water that is flowing in the bottom, out the top, and getting warmer as we go, as it is absorbing energy from our flash steam, condensing our flash steam, and then that condensate is being drained from the bottom of the unit to be recovered. Also worth noting here is that if we run into a scenario where the volume of flash steam that we have is greater than the condensing capability of this vent condenser, it's almost more likely that it's not all flash steam at that point. Maybe we've unintentionally opened a bypass valve or something that is sending an additional volume of steam into our return system, and we've overloaded our vent condenser. The design does allow for that excess steam to run through that center vent in the condenser there and be routed to the roof or wherever the vent is discharging. So at that point, we would condense everything the condenser is capable of condensing, and the remainder would be sent up the vent. Another comment worth making here is that to really maximize the benefit of installing a unit like this, we need to have a use for this cooling water that we're routing through the vent condenser. We don't want to send in cold water and turn it into hot water just to send it back to the cooling tower and lose all of that energy to atmosphere. That's what we were doing anyway. At that point, the only advantage is recovering some condensate back to the system. So depending on the facility and the water needs in that facility, there's a variety of sources that may be worthwhile. It could be boiler feed water or possibly processed water. But the important thing is that we have a use for this hot water. Let's take a look at some of the considerations when selecting a vent condenser for use. So we have a couple of models shown across the bottom of this chart here. We have the SR3, which can condense up to 660 pounds an hour of flash steam. And we have our SR8, which can condense anywhere between 0 and 1,760 pounds an hour of flash steam. So the first thing that we need to determine, how much flash steam do we have? How much do we want to condense? So for this example, let's say we have 1,000 pounds an hour of flash steam. And the next thing we have to determine is what is our desired cooling water outlet temperature. So let's say that temperature is somewhere between 150 and 160 degrees. So the result here is that in order to accomplish this goal, we would need 10,000 pounds an hour of cooling water. So now let's say that our goal is actually to minimize the amount of cooling water we want to use. So we're going to run this line all the way up, or alternatively, our goal is to maximize the cooling water outlet temperature. So at this point, we can discharge our cooling water at 200 degrees while only using 6,600 pounds an hour of cooling water instead of 10,000. Another consideration is going to be the maximum allowable flow rates through either of these units. So for the past example, we used 10,000 pounds an hour of cooling water. which you can see for the SR8 results in a pressure drop of only 8.6 psi, but a rather substantial pressure drop across the SR3. And that really is the maximum flow rate that we can achieve on the cooling water side through the SR3. So definitely something else that needs to be considered when selecting this product. So let's look at the installation of a SR series vent condenser, where there's a couple different variations. So this is the same installation that we saw in the model on the previous slides, where we're going to bring in two-phase flow, two-phase condensate and flash steam into a receiver. Condensate will be drained down to our PowerTrap, and the flash steam is going to be sent up the vent and routed to our vent condenser. It's also important to note that we can bring flows in from multiple receivers. So if we have more than one receiver in close vicinity to one another, we can route those vents to a common header and send multiple vents to a single vent condenser. And then from there, we condense that flash steam with our cooling water and send that condensate back down to our receiver, and then pump all of that back to our condensate return header to recover that condensate and the energy that is still in the condensate. An alternative installation looks something like this, where we're actually just routing the two-phase flow directly in and through our vent condenser. Other than that, it's pretty similar. We still have our cooling water in, our hot cooling water out, and we're going to drain all of that condensate directly down into our receiver to be pumped away by our PowerTrap back to our condensate return header. This is quite similar to the CDA that Drew showed you earlier, but only a different application. Instead of equipment drainage or specifically condensate recovery, this is the information that TLV would need to help with selection and installation recommendations for a vent condenser. So let's look at some of the economics behind recovering flash steam. So this diagram is a simplistic view showing the inflows and outflows of a system. We have our boiler supplying steam to our heat exchanger. We're going to drain that heat exchanger to a pump skid. We're going to vent the flash steam, and we're going to pump the condensate back to the boiler. So it's important to look at what is the system boundary here. What's actually coming in, what's actually going out. What happens inside that boundary doesn't make a whole lot of difference when it comes to dollars or energy savings. So the next slide here is basically the exact same thing. We still have our heat exchanger, we still have our condensate receiver that's being vented, and we're returning our condensate back to the boiler. So this is just an easier way to view all the flows. So our natural gas on the left has an energy value, the amount of energy we need to heat up and boil our water, turn it into steam, and supply it to our heat exchangers. We have a specific amount of makeup water that we have to bring back into the system. So that is a couple of our inflows. And then from our vent, we are discharging a specific quantity of energy, the EV, energy of our vent, and we're also discharging a specific quantity of water, the water from our vent. So if we install a vent condenser, you can see we've eliminated an outflow. That water content that we were losing is being drained back to our condensate receiver, sent back to the boiler, and the energy that we were losing is now in the form of hot water that we are also sending back to the boiler and keeping in our system. So before we had our energy content of natural gas, and we had our EV, which was the energy lost through the vent. So we can subtract our EV from our energy, which leads to dollars saved, less natural gas used, less energy needed to be supplied to our boiler. That results directly to dollars saved. And the same applies to less makeup water. We are now saving the water from the vent, and we can subtract that quantity from the water we're supplying from the makeup. So just going to run through a quick example of what these dollar savings would look like. So let's say we have a system, steam trap, where we got a differential of 140 psi, and at 140 psi pressure drop, that results in a flash rate of 13.72%. Let's say for the system, for this heat exchanger, we have a condensate load of 10,000 pounds an hour, which at that flash rate results in 1,372 pounds an hour of flash steam. Because there's a specific quantity of energy in each pound of that flash steam, it results in a little over 1.5 million BTUs per hour recovered. It's important to note that because we're recovering that water back into the system, that is that much less makeup water that we're bringing into the system. Makeup water is not very hot. It's only coming in at, let's call it 70 degrees, but there still is energy content there that we are not bringing into the system. So we have to subtract that from the total energy recovered, giving us our total energy saved of a bit less, still about 1.5 million BTUs. And assuming a steam cost of $6 per 1,000 pounds, that results in a dollar amount of a little over $9 saved an hour, and that can be extrapolated out to just under 80 grand a year, which really wouldn't be too bad of a return on investment for installing a piece of equipment like this. Okay, so last on our list for methods of recovering flash steam is utilizing a steam compressor, TLV SC series. So what is a steam compressor? Steam compressor is an ejector type equipment that will recover low pressure steam that was previously deemed too low of a pressure to be usable. And it can ramp up to a medium pressure steam for reuse. So the reuse of the steam can reduce fuel cost and CO2 emission. Similarly to a vent condenser, it's just the result is similar. We're keeping the energy in the system. It's just going about doing it in a different way. So what does this ejector system look like? What actually goes on here? We have a motive source, a high pressure steam source that is going to be sent through the inlet of our ejector. And we have our suction pressure, which is our low pressure steam, once being sent through a vent and rejected to atmosphere. And we're going to mix those two flows, resulting in a medium pressure steam, a usable medium pressure steam. So a closer look here, you can see the high pressure steam that's being sent through a nozzle. It's being sent through this nozzle at a very, very high velocity. And this high velocity results in a low pressure. That low pressure is actually sucking our low pressure steam up and mixing the flows. And as we bring those two flows together, it's resulting in a medium pressure steam, something that falls between the high pressure and the low pressure. So to walk through an example of how this would be applied in a real world situation. So if you see on the right there, we have some medium pressure steam using equipment. Our medium pressure steam header is at 2 bar, so it requires 2 bar to effectively supply our medium pressure steam equipment. And then we have our flash tank there that is only at 1 bar. So we don't have enough pressure to effectively send that flash steam to our medium pressure steam header. So currently it would be vented at atmosphere because we have no real use for it. Alternatively, if we install a steam ejector or a steam compressor, we can use high pressure steam, which is going to suck the low pressure steam up and mix the flows, resulting in a medium pressure usable steam. So that low pressure steam that was once being lost to atmosphere can now actually be maintained in the system and used in our medium pressure steam header. So that's energy kept in the system, which results in dollars saved. So this is just about the end of our presentation here. This presentation was brought to you by TLV CES Department, Consulting and Engineering Services. You can reach us anytime at our number shown on the screen there, 1-800-TLV-TRAP. There's always an engineer available to help support you in any of your STEAM needs, or you can email us at ces@tlvengineering.com. and one of our TLV engineers will get back to you. Alternatively, we have a lot of great resources, great references on our website, just tlv.com. We have the online calculator, which is extremely powerful, has many, many great uses, a lot of technical articles, and the webinar recordings, which will sooner than later include this one as well. So thank you very much. Appreciate you joining us today, and hope to see you guys for the next webinar.